Welcome to our university lecture on animal behavior. Today, we are diving into a truly fascinating and foundational topic called associative learning. We will explore exactly how animals, from household pets to wild birds, connect the dots in their environment to survive, thrive, and predict the future. Let us get started. To begin, let us think about a familiar experience. Imagine hearing the cheerful jingle of an ice cream truck. Even before you see it, your mouth might water. You were not born knowing this jingle means food. Instead, your brain made a connection over time. This everyday phenomenon is exactly what we call associative learning. It is the brain's remarkable way of linking two events that happen close together, allowing you to predict the future. Now that we understand the basic idea through our everyday experience, let us look at its formal scientific definition. In the study of animal behavior, associative learning is defined as any learning process in which a new response becomes associated with a particular stimulus. It is the fundamental mechanism through which an animal learns that one event reliably predicts another event in its environment. By forming these connections, the animal's nervous system physically wires itself to anticipate outcomes based on specific environmental cues. Building on that definition, there are two main types of associative learning that you will encounter in your studies. The first is classical conditioning, famously discovered by Ivan Pavlov. This involves pairing an involuntary biological response with a previously neutral stimulus, exactly like a dog learning to salivate at the sound of a bell. The second type is operant conditioning. On the other hand, this involves associating a voluntary behavior with a consequence, such as a rat learning to press a lever to receive a food pellet. Both processes are essential for adapting to new environments. Beyond laboratory experiments, like Pavlov's dogs, why does this concept matter so much in the wild? Associative learning is absolutely critical for an animal's survival and daily functioning. Without it, an animal would repeatedly make the same dangerous or wasteful mistakes. For example, if a bird eats a toxic, brightly colored butterfly, it needs to associate that specific color with feeling sick, so it never makes the mistake of eating one again. It allows animals to efficiently locate food, avoid predators, and navigate complex social environments. Having seen how vital this is for survival, you might wonder how we study it scientifically. While associative learning seems like a purely biological concept, scientists have actually developed rigorous mathematical models to describe exactly how it happens over time. The most famous of these is the Rescorla-Wagner model. By using this mathematical approach, researchers can calculate how the strength of an association between a stimulus and a reward changes with each new experience, turning abstract learning into measurable, predictable numbers. This brings us to the elegant equation at the heart of behavioral psychology, the Rescorla-Wagner model. Conceptually, this formula calculates how much an animal learns in a single moment. Let us break down the symbols. Delta V represents the change in associative strength during one trial. Alpha is the salience or noticeability of the stimulus, like how loud a bell is. Beta represents the learning rate tied to the reward, like how delicious the food is. If either the bell is louder or the food is tastier, the learning rate increases. Continuing with our formula, let us look at the terms inside the parentheses, which represent the core engine of learning. Lambda represents the maximum possible learning, or the total reward available. V is the current associative strength the animal already has before the trial begins. The difference between them, lambda minus V, is the surprise factor. In plain English, the amount of new learning depends on how surprising the reward is. If the reward is highly surprising, the animal learns a lot. As expectations match reality, surprise decreases and learning slows down. Now that we have our formula, let us see it in action with a concrete example. Imagine a dog hearing a bell for the very first time right before receiving a tasty treat. We are given the maximum associative strength, lambda, as 100. The noticeability, alpha, is 0.5, and the learning rate, beta, is 0.4. Because this is the first experience, the initial expectation, V, is 0. Let us solve this step by step. We substitute our values into the equation. First, we find the surprise factor inside the parentheses, which is 100 minus 0. Next, we multiply the learning rates outside to get 0.2. Finally, multiplying 0.2 by 100 gives our final answer of 20. Physically, this means after just one trial, the dog's expectation that the bell predicts food has jumped from 0 to 20. With the first trial complete, let us look at what happens during the dog's second lesson. The physical properties of the bell and treat have not changed, so alpha remains 0.5, beta is 0.4, and lambda is still 100. However, the critical difference is that the animal is no longer completely ignorant. Its current associative strength, V, is now 20. Let us plug these updated values into our formula. The term inside the parentheses is now 100 minus 20, meaning the surprise factor drops to 80. Our combined learning rate stays constant at 0.2. Multiplying 0.2 by 80 gives us a final change in associative strength of 16. Notice carefully that this new learning amount is less than the 20 learned in the first trial. As the animal gets better at predicting the event, the amount of new information it gains naturally decreases. To visualize what we just calculated, let us look at the Rescorla-Wagner learning curve. On the horizontal axis, we have the number of trials, and on the vertical axis, the associative strength, V. The dashed line at the top represents lambda, the maximum possible expectation. Notice how the solid blue curve starts at 0 and rises steeply during the first few trials, just like our dog jumping from 0 to 20, then to 36. As the trials continue, the curve flattens out, approaching the maximum limit. This beautifully illustrates that learning is fastest when surprise is high and slows down as mastery is achieved. We have covered the full topic of associative learning, so let us review our key takeaways. First, associative learning is the fundamental mechanism animals use to connect events and predict the future, which is absolutely vital for their survival. Second, we saw how the Rescorla-Wagner model translates this biological process into mathematics, showing us that learning is fundamentally driven by the element of surprise. Finally, we proved that learning happens fastest when an outcome is highly unexpected and naturally slows down as the animal's expectations match reality. Excellent work following along with these concepts and calculations.